All right, ladies and gentlemen, we'll get cracking on with today's talk. So grab a seat. If there's any arena people over there, jump over here. Hello, it's time for the morning lecture. Come on. Come on. Okay, cool. So today's material, optimization and hyperparameters, basically broken into three sections, one of which is we're going to be implementing a bunch of different optimizers from scratch. So this is the thing that actually decides to update the weights somehow based on the gradients. The second thing is we're going to be introducing a piece of tooling called weights and biases, which is basically a fantastic little dashboard for monitoring training runs, watching like loss curves go down live as they run. I'm sweeping over like multiple choices of different like hyperparameters. So if you like some sort of experiment, you want to tweak the hyperparameters for it, you can just let weights and biases run overnight and it will like try different values and show you like the performance is a function of like the learning rate or the batch size or the whatever. And the last material is on distributed training. So often when you have some training run, you might run into the problem where the model is too big to physically fit on one card. So you might shard the model across multiple cards. Or you have a model that can fit on one card, but you have lots of cards available. So you just want to like you want to use more GPUs to make the training job go faster. So we'll basically be talking about both of those things. So first off, basically a large chunk of today's material is just what's the magic stuff that lives in this bubble here. More or less, every optimizer has two methods you have to define. Step, which is here are the gradients, please do something to the parameters. And zero grad, which just like cleans out the gradients back to zero for the next forward pass. So the magic that happens here is what today's material will be. Optimization is broadly various clever forms of stochastic gradient descent. So by default, the simplest thing you can do is you have your loss function, you differentiate it as a function of the parameters, you take the parameters and you bump them in a little bit of direction downhill. So the gradient is always uphill. When we do gradient descent, we want loss to go down. We bump in a direction that's downhill. Our alpha here is our learning rate, which is just a hyperparameter that you have to choose. Choose too small, training takes too long to converge. Choose too big, you get like wildly big updates and you might diverge off to infinity. The material today has these like cutesy little low-dimensional plots of you got some annoying like loss landscape, some annoying surface, and you want to find like the global minima. So you'll like define your optimizer, SGD, RMS prop, Adam, whatever, and you'll like actually see what these optimizers do when you like step through the gradients. Now, these are pretty pictures, but intuitions don't really transfer that well from 2 dimensions to when you train a neural network, it might have literally 1 billion parameters. So like the loss landscape is like literally 1 billion dimensional space. Intuitions get fuzzy. Like when you have 1 billion dimensions, there's probably always a way downhill. So saddle points aren't nearly as big a deal. But this is nice for playing around with things, but like don't lean into this too much. Like this is not like a true description of like what training a neural network looks like. But it's nice to see like intuitively like what momentum does. What's momentum? So gradient descent methods often get stuck in local minima if you're just following always the direction downhill. So imagine like you're walking down a mountain and there's like a little tiny puddle halfway down the mountain and you're like stuck and you stand in the puddle and you get stuck there forever. This is obviously not good. If you're like running down the hill and you got like a fair bit of speed, you probably want to like jump out of the puddle. So momentum-based methods keep track of something called momentum, and on every step, the momentum is like increased by whatever direction is downhill. So the ball that's rolling down the hill picks up more and more and more speed. And you update in the direction not of the gradient, but of your current momentum. There's friction, which is called momentum decay, which is this term here, such that you don't keep rolling forever. Because once you like run into the global minima, you don't want to like run back out again. So the momentum like slowly decays off as a function of time, which is like essentially an exponentially weighted average, if that like means anything. And this is what like most gradient descent methods like Adam is like this with like extra special stuff on top. So on the little GIF here on the right, the blue ball is like gradient descent and the magenta ball is gradient descent with momentum. And you can see it skips out of the local minima. And then when it gets to the global minima, it kind of overshoots and rings a bit. So it like overshoots and then sort of gets stuck and then sort of spirals its way down as the momentum decays down to zero. So this helps with training basically for 2 reasons. One is you jump out of local minima. And two, use converge faster. If every time step you keep going downhill in the same direction, the ball rolls faster and faster and faster. So high level, that's what momentum is. Works pretty good. That's what we use. Weights and biases. Fantastic tool. Basically what it does is allows you to monitor training runs, allows you to run sweeps on multiple cards. So you like set up your training code, you set up your objective that you'd like to minimize, which is presumably like validation loss or maximize validation accuracy or something like that. And then you can spin up agents on either different cards or geographically separate machines, and weights and biases will allocate work to them. So each worker will be allocated, cool, here is your learning rate, here is your batch size, please do a training run. When the training run's finished, it'll report back to weights and biases, great, here was my loss, here is my training curves, blah, 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 blah. Weights and biases will then like give it more work to do. So you can just like spin this up and let it run overnight on some, I don't know, cluster with 1,000 GPUs, and you come back the next day to hopefully something useful out of all these different training runs. So great, here we're logging batch size and dropout and learning rate, and a whole bunch of all these different hyperparameters, and you can see like what the losses you get at the end of the day. And it'll also give you nice little features of here's how much these parameters matter to the loss and how they positively or negatively correlate. So this is like a fantastic tool for basically sweeping over a very high dimensional space of learning of hyperparameters for you in such a way that like you can try and tweak the learning rate or tweak the batch size to get like the best performance out of your model. So fantastic tool, would highly recommend it. And last thing is distributed training. So there's kind of like 3 high-level ways to do it if you want a training run to go faster. If it fits on the model, just have multiple copies of the model on multiple GPUs. You take your batch size. Let's say your batch size is like 100 batches of images. Each card gets 25 batches. You do a forward pass on each, and then you like average the gradients on all of them, and then all of them do a back prop at the same time. Sometimes this can actually be slower if the like latency between the cards is high, or if the bandwidth between the cards is high. So for like little tiny training runs, you like implement this and it actually ends up being worse than a single GPU because you're just moving junk back and forth. But for like sufficiently large models and sufficiently large amounts of compute, and assuming the bandwidth between them is pretty good, this like basically is a free speed up. Like 4 cards will be like almost 4 times as fast, ignoring the little like latency step at the end. For really, really big training runs, you can't fit arbitrarily many cards in like one rack. So you have like a rack with 8 cards, and then another rack connected by like some networking, and that's like a slower link. So like topologically it gets like more and more messy. Today you'll just have a single machine with 2 cards in it that are like physically plugged into the same machine. So it won't be too messy, but for like really big training runs, this becomes like quite a difficult problem, and like entire people's jobs is just like being the kind of engineer that works out how to like make all the GPUs happy if you have like 10,000 of them or something like that. So data parallelism, the simplest thing to do, you just multiple copies of the model, split the batches, aggregate the results. Pipeline parallelism is where you take the model and you shard it over multiple GPUs. Intuitively, this looks like you wouldn't get a speed boost because the blue part of the model has to wait for the yellow part to process, but you run this in a pipeline fashion. So when you feed through a batch, yellow processes it and feeds the batch to blue, and then while blue is processing something from batch 0, yellow can start processing something from batch 1. So imagine you have like an assembly line and you're like manufacturing cars. You don't have to wait for the first car to be painted before we start manufacturing the chassis for the second car. So hopefully all the GPUs can still be running, yeah?
But then if you do that, the previous batch would have updated the weights of that first part yet while there's already new.
Yeah, this gets messy with actually doing the gradient update. So usually what happens is you take your big batch and you split it up into little mini batches. You pipeline the forward passes, you wait till all that's propagated through, and then you do the backward pass afterwards. So there is going to be a region of time where the pipeline is like bubbled and empty, and there are like a whole bunch of papers on like trying to squeeze out these gaps of like, here's my like wacky optimization method. There's like forward passes here and backwards passes there, so all the GPUs are cooking as much as they can. This is like a very difficult engineering problem in general. But yes, the fact that like when you can't do a backward pass until all the forward is done, and so naively, yes, the pipeline will stall for a bit. And tensor parallelism, which we don't cover, but it's worth highlighting here, is a messy method where you basically take the weights themselves and factor them into chunks, and then you shard the chunks across the GPUs. I'm not quite sure exactly why I'd want to do this over pipeline parallelism. I guess because like you don't store things as bad. I'm not entirely sure, but it's a thing that exists, and so I'm pointing at it here.
It's your individual GPUs don't have that enough memory to hold one layer, and you might want to split things up further.
Okay, yeah. So I'm trying to think of a model where you'd have that problem, where like, yeah, I guess if you have like a transformer so large that even a single layer wouldn't fit. I guess one could, in principle, have this. If you had that problem, you could shard it in this way. This is usually pretty uncommon. Mainly these two, especially this one, is the most common thing to do, especially because this thing is super easy to implement, doesn't require that much changes. It requires no architectural changes to your model whatsoever. You just make multiple copies of it. This thing, there's a little bit of legwork to do, especially if your network doesn't easily factor into n equally sized chunks. If the yellow chunk is like really slow and the blue and the green chunks are very fast, you don't actually really gain that much. If you're like trying to think of I don't know, like you're making a recipe or whatever, and if like most of the time is baking it in the oven, you've only got one oven, then like all the other stages of the pipeline of someone mixing the ingredients is going to be stalled by the oven. So you actually don't gain anything unless you can cleanly factor the model into parts that roughly run in the same amount of time. That's all the slides I had to talk about. So now you should ask me some questions.
The machines that we currently have multiple GPUs?
Yes, for today you have a machine with two A4000 cards in it, which is the same machine as yesterday, but now it's got two cards in it.
Apart from the hotel machine, I haven't assigned anyone to that machine because that only has one card. So.
Okay. Yes, for today only, machines have two GPUs in them, both equally sized. Yeah.
I have a question on momentum.
Speak up.
Momentum.
Yes.
So you said there are two reasons for momentum. One is to not get stuck in the local minimum. One is to converge faster.
Yep.
I was on that first point, not getting stuck in local minima. Is that a real risk in a billion dimensional space? Can that happen? Did that happen? And was momentum solving that problem, or is it mostly about that second reason, converging faster?
So momentum is actually a pretty old technique when models didn't have like on order of billions of parameters, and yeah, you absolutely did get stuck in local minima. I suspect in practice, given it's such a high dimensional space, this would not be such a big concern, but without momentum, training is just so much slower. In practice, what's actually used is Adam, which is like a kind of a complicated optimizer that's like the last thing you implement today, that takes advantage of both the average and the variance of the empirically measured gradients, and it can learn from extremely noisy gradients in a way that both of these models struggle with a lot. And by default, Adam is just the go-to thing that you always use. There is also a hot new optimizer fresh off the press called Muon that I've highlighted as bonus material in the section because I don't know how it works. I've only briefly skimmed the Twitter thread about it. But that's there if you want to read the blog post for how it works. Some real nasty stuff. But in practice, it does way better, 40% gain in speed for training LLMs, which is crazy. Oopsies, capabilities. Cool. Any other questions? All right, get to it. Short and sweet. Oopsies.
You off?
My mouse is turned off, so it should be. Okay.